Hello everyone, welcome to a new lecture of our course on processing in memory. Today we are going to talk about another real-world processing in memory architecture, Samsung AxDIMM. Remember that we have covered a few of them, a few real-world processing in memory architectures until now, being the first one, the PIM architecture. Remember that this is composed by DDR4 DIMMs where the memory chips have been extended with DRAM processing units or DPUs. These DRAM processing units or DPUs are in order processors that are connected, each of them, to a DRAM bank, a 64 megabyte DRAM bank that is called MRAM. The DPU also has access to its instruction memory and also to SRAM-based scratchpad to store operands. Another architecture that we cover in this course is FIMM-DRAM, also called HB-PNM, that was proposed by Samsung, was presented by Samsung last year. This is based on HBM2 memory, where some of the DRAM layers have been modified to integrate PIM units or PIM compute units or PCUs, where each of the PIM units is connected to 2 memory banks. And each PIM unit is SIMD processor with 16 lanes, and they operate on 16-bit floating point operands. Similar proposal, in this case from SK Hynix, is accelerator in memory or AIM. But in this case, instead of using HBM2 memory, it's based on GDDR6 memory. In AIM, what we have is a processing unit connected to each of the memory banks. And in this processing unit, we have an array of 16 multipliers and another 3 to perform a reduction. One interesting novelty of these processing units as well is that they are able to execute activation functions, and they have interpolation logic to do so, and also the ability to access memory, to access lookup tables in memory to perform lookup table queries that contain or that retrieve the results of the activation functions. Another interesting thing in this architecture is that it has an SRAM-based global buffer, and it's possible to move data, to move between these global SRAM-based buffer and the DRAM banks. Today, we talk about a different type of proposal. This one is also from Samsung, and it's based on DIMM. So the DRAM DIMMs are extended with some sort of processing engine. This architecture was also announced last year in August 2021, and as you can see, it proposes to place an engine, a processing engine. In the announcement, it was called an AI engine inside the buffer chip of the DRAM DIMMs. The idea of this AxDIMM is to have processing in multiple banks at the same time, so exploiting rank level parallelism. And in principle, it has been prototyped and tested for recommendation systems, as we are going to see today. Here in this slide, you can see another view of the AxDIMMs, and also on the right-hand side, you can see the setup that they use in their paper for evaluation of this prototype. As you can see, they compare a baseline system with the AxDIMM system, where they have replaced the DIMMs in 2 of the memory channels with these AxDIMMs that contain a reconfigurable fabric or a small FPGA on them. And these FPGAs programmed to execute some operators that are necessary for the recommendation system. This is not the same work proposing the idea of extending DRAM DIMMs with some sort of processing engine or compute units. For example, this paper, Application Transparent Near Memory Processing Architecture with Memory Channel Network, presented in Micro 2018, proposed to extend a host processor with some DIMMs called MCN DIMMs. And in each of these DIMMs, you can see that together with the DRAM chips, there are some small processors. In particular, what they tested is ARM processors with 4 cores and their own last level cache. And these ARM processors can access their local DRAM, the chips, the DRAM chips in the own DIMM, but they can also communicate with the host processor by using this SRAM buffer. This is the paper that we are going to discuss today. This paper was published last year in IEEE Microjournal. The title of the paper, as you see, is Near Memory Processing in Action, Accelerating Personalized Recommendation with AxDIMM. And because, in principle, this AxDIMM architecture could support many other applications as well, but they have tested with recommendation systems, I think it's good to give a short introduction about the recommendation systems. The idea in a recommendation system is to find some candidate recommendations for users. They need to be retrieved and they need to be ranked in order to propose the most, in principle, those that will be most interesting recommendations for the users. So for example, in YouTube, we receive recommendations that are first obtained from the large corpus of videos that YouTube contains. First of all, it's important to, or it's necessary to generate some candidates to reduce the millions of videos that YouTube have to a number of hundreds of videos that are later ranked, and those tens or dozens of videos that are potentially more interesting for the user are ranked and proposed to the user based on the user history, the content, the context, and also the features of the videos. Here you can see another view of a similar system. First of all, we have this filtering model to find what are the candidate items, what are videos in YouTube, for example, that are later ranked, and we reduce the number of ranked items to the order of magnitude to a few tens or dozens. This filtering model and this ranking model look more or less, or may look more or less like this one that you can see in figure C. This is both for filtering and for ranking. And this one that you see here in figure C is based on the deep learning recommendation model that was proposed by Facebook in 2019. So we are going to focus on this DLRM recommendation system from Facebook. And here you can see a nicer picture of this model. As you can see, there are some dense features and there are some sparse features as well. We are going to see how these different types of features are handled and based on the queries that are received. In principle, we can work on multiple queries at the same time by increasing this batch size. For dense features, what recommendation models normally do is using multi-layer perceptron neural networks with fully connected layers. These dense features are continuous inputs in vectors and matrices, and as I said, typically processed by fully connected layers. These fully connected layers, especially when the batch size is large, are computation dominated, so they are mostly compute bound. We are going to see some characterization in an upcoming slide. For sparse features, these are for categorical inputs, and they are processed by indexing large embedding tables. So these embedding tables will reside in memory. They have millions of vectors, and it's necessary to look up and pulling operations to extract the representative sparse features that are learned during training. And in general, the operation that we see here is a gather reduce pattern. So we need to gather the features from the memory, from the embedding tables, and then perform a reduction operation. This reduction operation usually is performed as element-wise additions, as we will see. In the CAFE2, for example, in CAFE2 framework, for example, the operators that perform these gather reduce operations are called sparse lens or sparse length or SLS. And these are the operators that we are going to focus on today. But let's first characterize this DLRM recommendation system in order to identify what are the key performance bottlenecks in the different parts of this recommendation system. We consider in these plots here two different recommendation models, RMC1 and RMC2, and the operators used in these two recommendation models are SLS, the sparse length operators that I mentioned before, and FC are the fully connected layers of the DNNs. So as you can see in this figure on the left, as we increase the batch size, the analytical flops increase, and also the analytical memory bytes also increase. But as you can see as well here, the operational intensity remains pretty low in all cases, regardless of what's the batch size. So these sparse length operators have low FP intensity, and for larger batch size, they have higher memory footprint and higher memory intensity. And actually, we can also observe this bandwidth plot on the right-hand side, and we see that the memory bandwidth can easily be saturated by embedding operations, especially as both the batch size and the number of threads increase. So this demonstrates that these operators are memory bound, regardless of what's the number of, or especially when we increase the number of threads and when we increase the batch size. There have been several recent and interesting works providing or proposing near memory processing architecture for this type of recommendation systems and this type of operators with the idea, some of them based on DIMM-based architectures with the idea of exploiting rank level parallelism. So for example, this RecNMP architecture that was presented in MISCA 2020 proposes to extend the DIMM with some near memory processing units that are directly connected to the banks in order to access the embedding entries directly from the ranks and concurrently activate the ranks in order to exploit this parallelism, this rank level parallelism. Then the processing units in this near memory, so the near memory processing unit perform the local embedding lookup and pulling functions at the memory side, producing these general gather reduce execution patterns. So they access the embedding tables and then they perform the reduction and reduction operation before sending the results to the host. This operation is an element-wise summation of the embedding entries and is performed inside the processing unit, near memory processing unit, as I said, and the final polling result is transferred back to the host. AxDIMM follows, or at least the AxDIMM prototype for recommendation systems follows a different design, a similar design as we are going to see. But this AxDIMM, this accelerator DIMM, can be also used for other purposes as well. It's a DDR4 compatible FPGA-based platform with standard memory interfaces, and it can potentially support both in-order general purpose processors similar to the MCM paper that I mentioned before, and also specialized accelerator modules. In the end, it's an interesting prototyping platform for near memory processing and exploring different ways of doing near memory processing for different applications as well. In this particular lecture, we explain what this IEEE micro paper from last year presented. Is a personalized recommendation case study. In the paper, they explain the hardware implementation and the software stack support. So let's start describing this AxDIMM system. As I explained in the beginning, they compare to a baseline system where all computation is performed on the CPU, and in the AxDIMM system, they replace some regular DIMMs with these AxDIMMs that contain their own small FPGA that is going to perform the SLS operation. So this is why you see here SLS offload, because these SLS operators are offloaded to the near memory side. And this is another picture of the prototype. One interesting observation here is that in order to perform the experiments and the testing with this prototype, they had to slow down the system, reduce the frequency of the CPU in order to keep up with the FPGA speed, because FPGAs, as you know, run at a few hundred megahertz. If this was implemented in an ASIC, it could probably run at a significantly higher frequency, and it wouldn't be necessary to reduce the frequency of the CPU in a production setup, let's say. So let's talk about the hardware and architecture of this AxDIMM design. As you can see, the AxDIMM contains two ranks, rank 0 and rank 1, and it can be directly connected to the host processor using the standard DIMM interface. So it's from the point of view of the host processor is a regular DIMM, but this DIMM it contains also an FPGA, a reconfigurable fabric that can be used for near memory processing. And it's possible because there are two ranks, so it's possible to exploit rank level parallelism by creating like different near memory processing units that are going to operate on the different available ranks. In this case, we have two ranks on the DIMM. So it's going to be possible to access in parallel the embedding tables that will reside on the rank 0 and rank 1, and then perform the element-wise summation, the computation of the SLS operators inside the FPGA module. So here you can see another, picture of these near memory processing units near the rank. As you see, this one at the top corresponds to rank 0. This one at the bottom is connected to rank 1. And we are going to describe the different components of these near memory processing units. So first of all, the DIMM and the near memory processing units are connected to the host processor via the DDR4 interface. Through this DDR4 interface, the DIMM receives DRAM commands whenever it is needed to access the memory arrays in this rank 0 and rank 1, and also it's the DIMM is going to receive the near memory processing instructions that will be executed by the near memory processing units. These are received via the DQ pins from the host side. We can also identify here like these two memory interface generators that support the internal rank access between the RecNMP, the near memory processing unit, and the DRAM device. So they serve as the memory controller, kind of memory controller for the near memory processing units. We have to know, or you have to know, that there are two different modes of operation of these AxDIMMs. One is the non-acceleration mode. This is when the DIMM works as a regular DIMM that is accessed by the host processor to read and write data from the memory arrays. And then we have the acceleration mode that is blocking, because in the acceleration mode are the near memory processing units, the ones that access the memory, the data in the memory ranks in order to perform the whatever computation. In the particular case that we are studying today is the SLS operators. So they are blocking because during that time the host cannot access the memory ranks. And this is how the NMP instructions look like. You can see they are 64-bit instructions, and you can identify here the opcode for the different operations that the near memory processing unit support. We can also identify here row and column addresses for the addresses that are going to be accessed in the ranks and also these tags to for PSAM. This PSAM, as we are going to see now, is a buffer to store partial sums, and is composed by multiple registers that we also need to access to store partial results. As you see, the offloading is done by the host processor using read and write 64-bit read and write operations that need to be used by the host processor, for example, to write the instructions in these 256 kilobyte instruction buffer, where the instructions that are going to be executed by the near memory processing unit are going to be stored. This is the partial sum buffer that I mentioned before, of size 256 kilobyte as well, and it stores intermediate values for embedding pooling operations. And here we have also an instruction decoder to load and decode the NMP instructions that are fetched from the instruction buffer, and the command generator to issue read commands to the DRAM ranks and to the PSAM buffer before performing the additions in the other array that you see at the bottom of this command generator. As you can read as well in the slide, in one cycle, the command generator generates the command to fetch a burst of 64 bytes. And this is the other array, is composed by 16 floating point 32-bit others that perform element-wise summation of the loaded embedded entries and the PSAM vector. The way that the host processor can access these different registers that the near memory processing unit contains, and also the memory ranks, is by with its own memory mapping, this address map, where there are some reserved, as you see, there are some reserved addresses, but then there are also addresses to access the PSAM buffer, the registers that are there. There are some addresses reserved for the configuration register. There are some addresses reserved for the instruction buffer, and then the rest of the memory, the address space, is for the embedding tables residing in the ranks. Here on the right, you can see what are the different commands that the host processor can use or uses to access the different addresses of the memory map. So for example, for the PSAM buffer, because this one is going to contain the final one, contains partial results, but at the end of the execution will also contain the final result. These are the results are read by the host processor. The configuration registers can both be read or written by the processor, depending on the register and depending on what's the functionality of the register. We are going to see some of them in the next slides. And then instruction buffer, where the host processor writes the instructions, same as it has to write as well the embedding tables in the memory ranks. So let's take a quick look at how these AxDIMM accelerator works, these near memory processing units work, and how this execution flow takes place. So first of all, the host processor needs to load the embedding tables into the memory ranks. So this is done by using normal write operations to DRAM and using the non-acceleration mode in this case. And at this point, we have to change the mode. This is done by writing the corresponding register in the configuration registers, and also writing the instructions into the instruction buffer. Next, the host processor can launch the execution of the near memory processing kernel, the execution of the computation on the near memory side, on the near memory processing unit. To do so, it first needs to write the corresponding register in the configuration registers to start the execution, to signal the near memory processing units that they can start fetching instructions from the instruction buffer. And at that point, the execution of instructions starts here. So the execution of instructions follows a pipeline execution where first instructions are fetched and decoded by the decoder that the new memory processing unit contains. Then it's necessary to fetch data from the PSAM partial results, from the PSAM buffer, also from the embedding tables, then perform the addition on the other array, and finally write the results to the PSAM buffer. And these operations happen in consecutive cycles, but in reality, it's possible to access at the same time the contents of the PSAM buffer and the embedding tables that reside in the memory rank. During that time, the CPU as well is checking all the time this status register, which is one of the configuration registers, and that is the way for the near memory processing unit to signal the host processor when the execution of the near memory processing kernel has finished and all these instructions have been executed. When that happens, the host CPU can read the results that are stored, the results of the reduction of the element-wise summation that is in this PSAM buffer, and this is done by using a read operation, a read command. So this is the paper, Near Memory Processing in Action, Accelerating Personalized Recommendation with AxDIMM. You can find a few more details in the paper itself. And this is like, I would say, very interesting real-world processing in memory architecture with different possibilities as a prototype where we can place different types of accelerators in the FPGA, but also it would be possible to have like more general purpose processors like these ARM cores that the MCM paper proposed. So this is one of the real-world processing in memory architectures that we cover in this course. A different one that we cannot cover in detail is this NeuroBlade that is fabricating and commercializing an Israeli startup. This startup is fabricating chips that combine DRAM and thousands of cores. They use a GPU-like approach, and it's this architecture is targeted at big data analytics and AI. There is not much information about this architecture in their website or research papers, but I could find a couple of patents that explain more or less how, explain at least like a high-level view of the NeuroBlade system. It's a kind of distributed processor composed by memory arrays and processing arrays. In the processing arrays, we find processor subunits that are associated with memory banks. And these processor subunits can also be connected to other processor subunits in different ways with different network configurations. This is just one example configuration where we can see the memory instances and the corresponding processing subunits. We find 4 processing subunits in this figure, and they are connected all to all, as you see. And you can take a closer look at the processor subunits, memory instance, and in these processor subunits might be different types of processing elements and accelerators. As far as I could find in their website, they are commercializing this Xiphos appliance. It contains a x86 CPU and also SSDs, but more importantly, it has their PIM chips that they call PIM chips, I assume that they have memory arrays and also processing elements that they call intensive memory processing units. Something interesting here is that everything is connected on top of PCI Express fabric. So I assume that the connections between processor subunits that you have seen in the previous slide are based on PCI Express, but it's just some guess that I'm making here. NeuroBlade also comes with a software suite with their own API to program, their own compiler to generate the query execution plans. Remember that I mentioned before that this architecture is targeted at big data analytics, and they support TPC benchmarks and queries. Another interesting real-world processing in memory architecture that has been presented this year very recently in ISSCC conference is this logic to DRAM hybrid bonding with processing near memory engine for recommendation system. This has been presented by Alibaba, and we are going to talk about it in detail in our next lecture. But we can take a very quick look at the overall architecture. As you see, they are using a very interesting technique to do 3D stack chips where they are directly bonding using this hybrid bonding technique. Two dies, one of them is a DRAM die, the other one is a logic die, as you can also see in this illustration here. In the logic die, they incorporate not only the necessary controllers to access, memory controllers to access DRAM, but also some IP blocks that are called neural engine and match engine, and they are specifically designed for the recommendation system that they have implemented. As we will see in the next lecture, this quartz green matching that, according to my understanding, is similar to the filtering that I mentioned in the beginning of the lecture. The filtering model that I mentioned in the beginning of the lecture is executed on the match engine, while the fine-grained ranking that corresponds to the ranking that we discussed in the beginning is executed in this neural engine. But we will see all the details in the next lecture. And also in future lectures as well, we will cover other types of processing in memory architecture, in particular processing using memory architectures and frameworks and prototypes that already exist, together with other works that are necessary and important to enable the adoption of processing in memory in real systems. This is all for today. I hope that you found the lecture interesting. Please don't hesitate to contact me if you need to ask any questions or discuss anything related to the lecture or the course. And I hope to see you in the next lecture of our Processing in Memory course. Thank you very much for your attention.